All right, everyone. Welcome again to another one of Mr. Martin's math videos. This video is for our British Columbia Pre-Calculus 12. We're looking at Chapter 6, Section 4, solving trigonometric equations using identities. All right, so now we're going to be putting our identity skills to good use, really combining everything from this entire unit, not just in this entire chapter, all together. We're going to be using unit circle, we're going to be solving trig equations, and we're going to be simplifying those equations using our identities. So everything's going to come together here for this section, which is fitting because it's the last section of not just the chapter, but also the unit. So let's get started here with a little flow chart to kind of help us know the direction to take with these equations. So we're going to first start off, we're going to be given some kind of crazy looking equation, and we're going to take that crazy looking equation and we're going to use identities to make it look a little less crazy, and then at that point we're going to simplify to one of the three primary trig ratios and we're going to factor the equation. All right, so let's just jump in. This set of notes is like all examples, right? There's no real new topic that or kind of concept we're presenting. The biggest thing is just kind of how do we bring all of these things together. Okay, so for these first ones we're going to solve for a specific domain, but you should read this and kind of be expecting that eventually we're going to be solving for general equations as well for solutions, right, given the repetitious nature of trig functions or trig graphs. So solve each equation algebraically over the domain 0 is less than or equal to x, which is less than or equal to 2 or less than 2 pi. So let's take a look. We have this equation here, cos 2x plus 1x minus cos x is equal to 0. And here I'm going to have my kind of trig identities notes handy as well, or my formula sheet, so I can kind of remember some of my identities that I can use to simplify this equation. So we want to rewrite this formula so that all the arguments inside the cosine function are just x. Okay, we don't want any kind of these double angles involved here. So, but at the same time, because I'm solving an equation, I don't want to introduce sine or tan into here unless I don't have to, right? And so for that reason, when I start off with cos 2x plus 1 minus cos x is equal to a, okay, I'm going to substitute cos 2x with the one that only has cos in it, no sine or anything else. And so I'm going to get 2 cos squared x minus 1, okay? That's going to substitute in for the cos 2x, and then plus 1, and then minus cos x is equal to 0. Okay? So now let's simplify this further. So now everything's in cos, no double angles in sight. So let's see what we end up with here. So there's no multiplication, so we don't have to worry about the brackets. The plus 1, minus 1 end up canceling each other out. And so that's going to leave me with 2 cos squared x minus cos x is equal to 0. Now here, because I don't have anything in the denominator, I don't have any non-permissible values, but you do want to be thinking about non-permissible values in some of these. If you have a tan ratio or anything with a denominator, then you have to be considering non-permissible values. But we'll be looking at the examples of that when we get there. So now how do I factor this? Okay, well here I have a greatest common factor here of cos. So cos x I can factor out, and I end up with 2 cos x minus 1 is equal to 0. Okay? So now these are both factored, right? And both of these equal to 0, but the product of these equal to 0. That means that either of them individually, if they equal to 0, the whole thing equals to 0. So I can have, I can split the equation there at this stage into cos x is equal to 0 and 2 cos x minus 1 is equal to 0. And then from there I can solve for x. So what values of x would equal 0 here on our unit circle. Where on the unit circle does cos, or our x variable, our x coordinate on the unit circle, equals 0? Okay, well, our two solutions should be pi over 2 and at 3 pi over 2, right? That's when cos x is equal to 0. So those would be the two solutions for on this side. On this other side, a little bit of algebra. I'm going to add 1 to both sides and then divide both sides by 2. And I'm going to get cos x is equal to 1 over 2. So again, on the unit circle, where is cos x, the x value on the unit circle, on the coordinates on the unit circle, equal to 1/2? Okay, and this would give me pi over 3. I'll give you a second to get your unit circle out as well in your formula sheet. You want to have all these things out so you have the tools you need to be successful for. So pi over 3, and again at 5 pi over 3, right? Again, here this is where is cos x equal to positive 1/2, not negative 1/2. So this would only happen in quadrants 1 and 4, according to the cast rule. Okay, and then all of these solutions fit within our domain, right? And so that would be our final answer. Here and here. These would be our final answer. Okay? So we use the trig identity to simplify an equation. And then from last chapter, we used that equation to solve for, to algebraically simplify that equation. And then we used our unit circle from chapter 4 to be able to identify where on the unit circle that degree in radians in order to get the solutions for the equation. Okay, so bringing everything together, beautiful thing. All right, next page here. Here's a common mistake that students fall into. It's very common for algebra. We talked about this in grade 11, but we're gonna do a quick check here to make sure that we're not losing out on some answers here. So way back in grade 11, with me real quick and solve the following equations. So in this situation, the correct way to factor this, right, would be to find to solve for this would be a greatest common factor, which would be x, right? And so I would get x, and then this would be x minus 3 is equal to 0. And then this would give me two solutions, right? It would give me x is equal to 0 and x minus 3 is equal to 0, which we would say x is equal to 3, right? So we'd have two solutions. Okay? However, there's a common mistake that students make here. Instead of factoring the equal sign, okay, in this equation, this is what they end up doing, okay, where you have x squared minus 3x is equal to 0, and then they add 3x to both sides, plus 3x, which gives me x squared is equal to 3x, okay, and then you can divide both sides by x, and then you end up with x is equal to 3, right? So here you only get one solution, all right? Whereas on the top here we got two solutions. Correctly, we got two solutions. Where on the bottom, we incorrectly got one solution, just one solution, okay? So what went wrong here? Here we want to be careful when you're dividing any expression that has an x in it. You could eliminate potential answers like we saw in this second example here. This is wrong, and right, this is wrong, and this is right. To make that clear in the notes, okay? So yeah, when you're simplifying as much as possible, you only divide by an expression that has an x in it when the original question divides by that expression. Okay, so you wouldn't go and find additional, kind of expressions to divide by x, you only use it if it's there. You only divide by the variable if it's already there in the denominator. Okay, otherwise you want to be factoring to find your solutions, or else you end up losing out, right? You would get 50% for this answer because you've only got half the answer. You've only done half the work. Okay, so keep that in mind. Be watching out for that. So let's do another example here. So here we want to solve the problem cos 2x is equal to cotangent x times sine x. Okay, and again here I'm looking for domain of 0 to 360. So my solution should be in degrees here instead of radians. So I have cos 2x is equal to cotangent x times sine x. Okay, first thing I want to do always is turn everything into sines and cosines, okay, in order to simplify this. So this is already in cosine, so there's nothing to do here. Cotangent is going to change to cos x over sine x times sine x. Okay, now here you can see that this cancels out. Sine x times sine x over 1, right? When you multiply by sine x. Okay. All right, which is going to give me cos 2x is equal to cos x. Okay. Now here I don't want to, I'm going to pause here. Not pause the video, but I'm going to leave it as is here. But first I want to look at non-permissible values, right? Because we did have a denominator for, a moment in this question, sine x. So we know that in this question, we have some non-permissible values, right? Because if sine x is equal to 0, then that cotangent is undefined, and then the whole question becomes unsolvable. So here I know that sine x cannot equal 0. And where does sine x, at what angle of x is sine x equal to 0? And that would be, where does the y equal to 0? It's equal to 0 at 0, and 0 degrees and 180 degrees. Okay, so x cannot equal 0 degrees and it cannot equal 180 degrees. Do I need to include the 360 degrees in this? The answer is no, right? Because here this is less than, not less than or equal to, so I don't have to include the 360. But if it was less than or equal to, then I would have to include the 360. Okay, so x cannot equal 0 or 180. Good. All right. Now from here, I'm not going to, inverse sine both sides or do anything like that. I'm going to subtract cos x on both sides. Bring everything, and I want my equation to equal to 0. That's what you want, right? When you're solving for equations, back from pre-calc 11, that's what we always wanted. Cos squared x minus cos x is equal to 0. And then we can factor this, right? I'm going to factor out cos x, which leaves me with cos x minus 1 is equal to 0. And then from here, I can solve for all of my solutions, right? This can split into cos x is equal to 0 and cos x minus 1 is equal to 0. Okay, so what degrees does cos x equal 0? Well, in degrees, that's 90 degrees and 270 degrees. Cos x is equal to 0. All right. Now for this side, I'm going to add 1 to both sides. And that's going to give me cos x is equal to 1. So where is cos x equal to 1? Well, that happens at 0 degrees and 180 degrees. Okay. However, so we know that this is solutions for sure. Here, these solutions, lo and behold, are non-permissible values, right? So these ones are actually not solutions because they are non-permissible values. That's the importance of finding all non-permissible values. But that's an example of, again, we're not, dividing by cos or x or anything in this question. We're bringing everything over to make it equal to 0, this step here. And then we can go ahead and factor and solve from there. Okay? But not neglecting our non-permissible values. All right, so that would be our answer for that example. Okay, that's essentially the instruction for today. Literally, the rest of the notes is a few more examples, and then that's it. And so, I want you guys. I'm going to kind of scroll through all of the questions that you have to do. So there's 6 of them, I think. These are the first 3, and then the next 2, and then the last one, which is finding the general solution. I think for the previous one, yeah, finding the general solution for E. Okay, so go ahead and pause the video, go through the video to be able to answer all the questions on your own. Get as far as you can for every single one of these. You'll be happy you did, and then we'll come back and solve all these together. All right, hopefully that went well for you. So let's get started. Okay, here we have tan. Okay, well, right away for tan, I'm going to change everything into sine and cos, right? So I'm going to get sine squared x. Actually, no, I don't have to do that. I can solve for tan in these equations as well. Okay, however, you do have to realize that you do have tan x is equal to sine x over cos x. And so you do have some undefined values here, non-permissible values. All right, where cos x cannot equal to 0. And we're in radians here. So where does, on our unit circle, at what degrees in radian does cos x equal 0? Well, that is at pi over 2 and 3 pi over 2. All right, so those are 2 non-permissible values. All right, but otherwise we can just stay in tan. And so here I'm going to factor out tan. That leaves me with tan x minus 1 is equal to 0. Okay, and so here tan x is equal to 0. And it splits in 2, right? And tan x tax. Tan x minus 1 is equal to 0. Okay, and I'll do plus 1 right here real quick just to finish that off. Tan x is equal to 1. All right, so for our solutions, where on the unit circle is tan x equal to 0? The ratio of y over x, but not undefined. Okay, that's an important point, because if your point is undefined, then you have a problem, right? Because, if your y is 0 and your x is a number other than 0, you're fine. But if your x is 0, then it's undefined. And so here, and that's also given to us right here, right, in our non-permissible values. That is exactly what it gives us. So here, 2 values for radians is 0 radian and pi. Okay, that's 2 places on the unit circle where tan is equal to 0. Okay, and where on the unit circle is tan x equal to 1? Positive 1. Okay, this is where the y and the x value would equal to each other, right? Tan theta is equal to y over x, and if y is equal to x, right, then tan theta or tan x is equal to 1. So this happens at pi over 4, and in the third quadrant, 5 pi over 4. Okay, and these would be the only 4 solutions inside of my domain. So that would be my final answer. Okay. All right. Let's try another one. Here, doesn't look like we're going to have any denominators in this one, so we don't have to worry about non-permissible values. We do have a double angle that we want to get rid of here. So let's start with that. And of course, the sine 2x only has one double angle kind of rule to it. So I'm going to substitute sine 2x with 2 sine x cos x minus sine x is equal to 0. All right. And here I have a greatest common factor, so I'm going to go ahead and factor that out, right? My greatest common factor is sine x, which leaves me with 2 cos x minus 1. Okay, now even though here they're not both cos or they're not both sine, you can still solve it. Because in this situation, you can still split this into the two factors, right? So if sine x is equal to 0, then my equation is equal to 0. Or if 2 cos x minus 1 is equal to 0, that my equation is also going to equal to 0. So they don't have to both be sine or both be cos. Typically, when you're simplifying it, if you can kind of work towards making them the same, it's typically simpler, but it doesn't have to be, okay? So in this situation, where is sine x equal to 0? Where are the y values equal to 0 on our unit circle? Okay, well, here I'm working in radian or degrees? Radian. So this is true at 0 and pi, right? At 0 and pi. Over here, quick algebra here, cos x is equal to 1 over 2. Where on the unit circle is cos x is equal to 1 over 2? At what degrees in radian is cos x equal to 1 over 2? So our x variable, x component of our coordinate on the unit circle is equal to 1/2 at pi over 3 in quadrant 1 and 5 pi over 3 in quadrant 4, right? Cast rule, cos is positive in quadrants 1 and quadrant 4. So we have our two solutions. No non-permissible values, 4 solutions, and all of these values fit within our domain, and there aren't any additional values that we could add just by adding the period, okay? Good stuff, good start. All right, let's try another one here. Here, again, we have a double angle, so let's start with that. So this is going to give me 2 sine x cos x is equal to pi square root 2 cos x. Okay. So here, what we can, let's bring everything and make our equation equal to 0. Okay, let's do that first. All right, so I'm going to bring minus square root 2 cos x minus square root 2 cos x. Okay. And that's going to equal 0 on this side, and I'm going to have 2 sine x cos x minus square root 2 cos x. Now, is there a greatest common factor here? Yes, there is. I can factor out cos x, and I would be left with 2 sine x minus square root 2 is equal to 0. Okay, and then here I can start splitting. I can split up my equation right from there, right? So on this side I have cos. Do I have any denominators in this question? No, I don't. So I don't have to worry about non-permissible values. So cos x is equal to 0 over here, whereas cos x equal to 0. The x variable is equal to 0 at 90 degrees. Oh, sorry, I'm in radians. So not 90 degrees. Pi over 2 and 3 pi over 2. Okay. And what about this one here? We have sine, but here the square root 2, it might seem like it's odd, but when we think about the unit circle, it actually fits right in with some of the coordinates we know of the unit circle, especially if we give it, especially once we simplify it and isolate the sine x in this, right? You'll see it right away. So this is 2 sine x minus square root 2 is equal to 0. I'm going to add square root 2 on both sides, and then I'm going to divide both sides by 2, and I'm going to get sine x is equal to square root 2 over 2. Does that look familiar? I'm hoping that's a resounding yes that I'm hearing in the void. Okay, and so where would this be true? Okay, whereas sine x, of course, it's in quadrants 1 and 2 because it's a sine function. Okay, and it would be at pi over 4, where sine, or the x and y value are both equal to root 2 over 2. So pi over 2, pi over 4. And in quadrant 2, this would be what, 3 pi over 2? 3 pi over 4, because it's still less than pi. And that's it. Those are our 4 solutions for this question. Okay? Some of you guys may have started off by dividing cos on both sides. Then that would have maybe solved an initial problem because you crossed off cos on the left side and the right side. However, what I imagine you both realized, or that you realized after doing that, is you did exactly what we told you, or I told you not to do on this page here, right? You actually got rid of half of your solutions by doing that. So it's important that you don't do that. You subtract square root 2 cos x on both sides, make it all equal to 0, and then go to work from there. Okay? No non-permissible values. We're done. We're done. All right. So let's take a look here at general solutions for this problem. So here, general solutions for this problem. So if I didn't have a limited domain of this, what would be my general solutions? Okay. Well, I have pi over 2, right? So x is equal to pi over 2. And my next solution is pi away from that. And every subsequent solution would be pi away from that, either in the positive or negative direction. Okay, so that's one of my, of course, all of these are going to be with n being an integer, okay, but I'll add that at the very end to all 3. Another one is pi over 4. Okay, when's the next time this happens? This happens, pi over 4 happens pi over 2 in the very next quadrant, right? However, if I put plus pi over 2n, I would be correct for the immediate one afterwards, right? Pi over 4 plus pi over 2 would give me 3 pi over 2, 3 pi over 4. However, the following solution I would get would be 7 pi over 4. And that's not, no, it wouldn't be 7 pi over 4. It would be 5 pi over 4. And that's not a correct answer. Okay? So we can't use this. Okay? Because our cos solutions, right, if this is our quadrant, they show up here and here. I can find the difference between this and this, but that same difference does not hold true for the rest of the unit circle. So I need to come up with 2 separate general solutions, okay? One for this solution and one for this solution, okay? And each of them, I'm going to have 2 pi between them. So I'm just going to go a whole circle around until it keeps landing on that spot. All right? So this is going to be 2 pi n, and then 3 pi over 4, also plus 2 pi n. Okay? And all of these, of course, and we understand are integers. Okay? So those would be the 3 general solutions that you would have to have for the previous answers there. All right, rewatch that. If you need to think about it, right, this solution here, essentially what we're doing is we're taking the solution and then just adding 2 pi each time to get back to future solutions. And same thing for this one. We're adding 2 pi to find future solutions for that one as well. All right, so hopefully that makes sense and that diagram is not too messy. to be helpful. All right, last question, and then we just find a general solution for this question as well. So I start off with sine. Awesome, everything's look good. I will end up with a denominator for this one here. So keep that in mind as you're doing this question here. So 2 sine x, everything's good there. I'm not gonna, worry about that one too much. It's already in sine, so I'm gonna get 2 sine x is equal to 7 minus, and this is going to be 3 over sine x, right? Because it's 3 times 1 over sine x, which is 3 over sine x, okay? So let me just make that in red so that you know that it has been substituted for cosecant. Okay, now that sine x is in the denominator position, so I got some non-permissible values, right? Sine x can't equal to 0, or else my equation is going to be undefined. So where is sine x equal to 0? Because then we just have to find solutions that aren't there. So sine x is equal to 0 at 0 and at pi, according to our domain, right? So x cannot equal these two things. All right, we got our non-permissible values. Let's keep going here. All right. So at this stage, I'm going to bring everything over to the left-hand side, make my equation equal to 0. Okay, so that means I'm going to be subtracting 7 on both sides, and I'm going to be adding 3 pi over sine x, or sorry, just 3 over sine x on both sides. Okay, so that's minus 7, and then plus 3 over sine x. And that's going to give me 2 sine x minus 7 plus 3 over sine x is equal to 0. Okay, well, I got all kinds of stuff going on here now. But how can I add all of these things together? Well, I can get a common denominator for one, right? And so let's do that, right? So I'm going to get a common denominator, multiply, because these are over 1. Let me do it different. This is over 1, this is over 1. So if I multiply sine to the top and bottom of each of these, I'm going to get 2 sine squared x over sine x, and then minus 7 sine x over sine x, then plus 3 sine x equals 0. Okay, so now I got some common denominators there. And from here, if I multiply both sides by sine x, multiply both sides of my equation by sine x, that gets rid of my denominator. So I'm left with the equation 2 sine squared x minus 7 sine x plus 3 is equal to 0. Okay? Now I've gotten somewhere, right? I've gotten to an equation that looks like a quadratic equation, or like a trinomial that I can factor. And indeed, I can factor this, right? If I can use the A method, in fact, right? If you guys remember the A method, if I say that sine x is equal to A, I'm going to substitute A for all of these places, right? So I am going to end up with 2A squared minus 7A plus 3 is equal to 0. Okay, and I factor this. My magic number, 2 times 3 is 6. So the factor that I have needs to be a product of 6 and a sum of negative 7. All right, so number that's a product is 6 and the sum is negative 7. It's negative 1 and negative 3. Okay, or negative 6. So I'm going to split my center value here into negative 1a and negative 6a. And that's going to give me 2a squared minus that, then minus, put that in red, minus 6a plus 3 is equal to 0. I'm going to group these up, and I factor out common factor, greatest common factor. So here my greatest common factor is just a. I'm left with 2a minus 1. Here my greatest common factor is 3. And I'm going to factor out negative 3 here, negative 3, which gives me 2a minus 1. So my two factors are a minus 3 and 2a minus 1 is equal to 0. And now I can resubstitute sine back into my equation, right? So I end up with sine x minus 3. Let me put that in red so that you can see the resubstitution of sine x. And of course, this was this. This is right. Okay. And 2 minus 1, and then I have 2 sine x minus 1 is equal to 0. All right. Now I'm at a stage where I can just split up and try to solve for some of these. Okay. So here, first of all, sine x minus 3 is equal to 0, plus 3 sine x is equal to 3. Where on the unit circle is sine x? At what angle would sine x be equal to 3? Hopefully your answer is there is no possible answers there. There's no place where sine x for the y value would be equal to 3 on your unit circle, because it's a unit circle. The highest value will ever only be a 1 or 1 unit, okay? Unit singular circle, okay? So in this situation, no possible solutions for x on that one, all right? But for the other one, 2 sine x minus 1 is equal to 0, plus 1 divided by 2 sine x is equal to 1 over 2. Where on your unit circle is sine x equal to 1 over 2? X is equal to, sine x is equal to 1/2, where? At pi over 6. And where else? Sine is going to be positive in the unit, in the second quadrant, and it's going to be pi over 6 before pi, so it's going to be 5 pi over 6. So those are my only two solutions here for this. All right. But again, just like the last question, for general solution, we have to be mindful. We can't just do like pi over 6, pi plus pi, and just assume we're right. So here, give the general solution. So x is equal, I know that's equal to pi over 6, okay? And I know that 5 pi over 6 is 4 pi over 6 away from pi over 6, right? However, if you add another 4 pi over 6, or 2 pi over 3 if you want to simplify, you don't get a solution. So you can apply that once, but it won't give you perpetual solutions like a general solution needs to give you. So you need to come up with separate general solution statements for your two spots, right? Just like the kind of little diagram I drew last time, one of my solutions is here, one of my solutions is here, okay? Here, this is a difference of 2 pi over 3, or 4 pi over 2, or 6. So that would seem like, okay, I can go up by 2 pi over 3 times n, but that's not the case, because your next solution then would be like over here somewhere, right? And this is not a solution, okay? So you need to find a solution for the green one, your first location, and then just add 2 pi to that repeatedly.
And then you need to define a general solution for the blue highlighted arrow, and then just add 2 pi repeatedly to that for your general solution, which is what we're going to do here. 2 pi n, 2 pi n, and also understanding that n here are integers, all positive and negative numbers without decimals. Okay, so that would be your general solutions. That is your notes. That is your chapter. That is your unit. And this is your homework. Hopefully this video is helpful for you. Watch it, rewatch it, and ask questions in the Teams channel if you have any along the way. Good luck, and we'll see you next class. Goodbye.